Hi everyone. Alright, so this will be our video for the Unit 6 questions out of the final review packet. If you missed the questions from Unit 5, that's a separate video, but we'll be starting with question 8 in the final review packet. So, the first question asks you to show the three light equations we discussed in class. So as it says, there were three. So the three of them are this one. Here's one, here's two, and here's three. Oops, sorry, I made a mistake there. That should actually be this one. There we go. And then here's the third. Okay, all three of these are in the reference book, so if you forget what they mean, please feel free to check those out or look at them during the test. But if we check out our variables, we should definitely know what they mean. So C right here is the speed of light. It is a constant. It's always 3 times 10 to the 8th meters per second, also in the reference book. So you don't need to memorize it. This variable here, move my hand there we go, that's the wavelength. And this variable here is the frequency. Okay. In our other equations, you'll also see some similar variables. So you see frequency again right there. This is also a constant. It's Planck's constant. The number is in the reference book as well. It's 6.626 times 10 to the negative 34th joules times seconds. And then E would be energy. In our final equation, you see all three of those again. So you see energy, you see Planck's constant, you see the speed of light, and you see wavelength. So 4 different things, actually. Okay? So you'll be using these for some of those later questions. The last part of the question asks you to state the relationship between frequency and wavelength and then the speed of light. So based on our equation right here, if we take a look, frequency and wavelength are on the same side of the equation, meaning if this one goes up, this one must go down to keep it equal to the same number. So we can say that frequency and wavelength are inversely proportional. As we saw with our gas laws, that means one goes up and one goes down. Okay, and then the speed of light, if we compare those, we can see that since this is on the opposite side of the equation from this, that means they're direct. So if this went up, that would go up, if this went up, that went up. But our speed of light really isn't going to change too much since it is a constant, right? If we look at our other equations over here, energy and frequency are on opposite sides, so if this goes up, that goes up. So those two are directly related, energy and frequency. So I'll add that to our last part down here. So energy and frequency are directly proportional. Alright, so there's question 8. You'll be using these formulas in some of them in question 9, I believe. Or no, I lied, 15. Now to question 9. So determine the number of electrons occupying the p orbitals in the arsenic atom, and as you read through this, this is really our question dealing with electronic structure. Okay? So the first thing, it's talking about the arsenic atom, so the first thing you really should do is write the electron configuration for this, right? So if you write the electron configuration for arsenic, it's pretty far down the periodic table, but if we were to write this whole thing, it would be 1s2, 2s2, 2p6, 3s2, etc. So I'll just write all this out for you. You'll see some questions with electron configurations later in the packet. Oops, it might have gone too far. Not 4p6, should be 4p3. So if it wants the total number of electrons occupying p orbitals, we just need to count up our exponents. So 6, and another 6, and then 3. So altogether, that would give you a grand total of 15 electrons in the p orbital. So there's your answer for part A. Part B, it says how many orbitals are in the third energy level. Keep in mind, orbitals make up sublevels. So every s sublevel has 2 orbitals, every p sublevel, excuse me, made a mistake again. There we go. Every S sublevel has 1 orbital. P sublevels have 3. Ds have 5. Fs have 7. So the question is, in the third energy level, are all 4 of these present or just some of them? If you look at the periodic table in the third row, it looks like you only have the S and the P sublevel. However, we know that the D sublevel is actually sneaky. We write it as 1 row less than where it appears. So that first D sublevel, which is in the 4th row, really is 3D. So what we have would be the 1, the 3, and the 5, so that would give you 9 orbitals total. There is no 3F. Okay. For C, how many d orbitals are in a d sublevel? We kind of already answered this up above in part B. There are 5 orbitals in every d sublevel, which is why it can hold 10 electrons. There we go. And then our last one, how many valence electrons are in an atom of sulfur? So the trick here, remember we said it's the same as the last digit in the group number. So if sulfur is in group 16, which it is, that means it would have 6 valence electrons. The other way you could do it is if you look at the electron configuration. The electron configuration for sulfur, if we do the noble gas configuration, would be this. And 2 plus 6, notice, still does give you 6 valence electrons. Okay? So, moving to question 10. 10 and 11 are very specific, but 10 says define the term isoelectronic. So hopefully if you weren't quite sure what that was, you could Google it. We did talk about it, but very, very briefly. But 2 things that are isoelectronic means you have 2 species, so 2 substances, basically, with the same number of electrons. Okay? So, as an example, neon and the fluoride ion, which would be F minus 1, both have 10 electrons. So we would say that they are isoelectronic. Okay. Looking at 11 then, it says what ion with a charge of -2 is isoelectronic with argon. So the first thing we should figure out is how many electrons does argon have. If you look on the periodic table, argon is the 18th element, which means it has 18 protons in its nucleus, and if we're talking about a neutral atom, it also has 18 electrons. So the question becomes, which ion with a charge of -2 also would have 18 electrons? If we look on our periodic table, all of the ions that form -2 charges are in group 16. So if we narrow it down from group 16, we see that oxygen has 8 electrons when it's neutral, so adding 2 to that would make it 10. Sulfur has 16 electrons when it's neutral, so to get that -2 charge, if it gains 2 electrons, it would have 18 electrons. So the sulfide ion would be isoelectronic with a neutral argon atom. Because they both would have 18 electrons. Argon would have 18 protons and 18 neutrons. Sulfur over here, the sulfide ion, would have 16 protons but 18 electrons. So, moving into question 12, here's where we see our electron configurations. Okay, so just as a refresher, let me pull up the periodic table here. Alright, so here's our periodic table. Just a quick refresher about our electron configurations. So there are 3 parts to every electron configuration. Just as an example, you have a coefficient, oops, one sec. There we go. You have a coefficient, a letter, and a number. Right, so there's an example. The coefficient always corresponds with the energy level, what it actually represents, but on the periodic table it corresponds to the row number you're in. The letter corresponds to the sublevel, but on our periodic table it corresponds to certain areas. Remember we said that over here, these were all the S sublevels, including this one up here. This square over here were the P sublevels. This middle section here, this was the D sublevels, and then these 2 rows at the bottom would be the F sublevels. Okay? So, keeping all that in mind, the last piece was the exponent. The exponent is how many electrons are in a particular sublevel, but it corresponds on our periodic table to how many spots you move within a section. So, 3 spots, 4 spots, 5 spots, 6 spots, etc. Okay? So, for this section, I suggest you have a periodic table handy if you don't already have one near you. So you can take that out, and then we'll go through. I'll try and talk our way through the questions, but it's going to be easiest if you're following along on your periodic table as we go through this. Alright, so starting with an aluminum atom. If it's neutral, we're just basically going to go along our periodic table until we get down to here. Okay, so if we start our way along, first thing would be 1. We need to do this whole first row. So 1, both of those were S, we get 2, so that would give us 1s2. That would take care of hydrogen and helium. Next up, we would be in row 2, so we have to do this entire row. These 2 would be 2, because we're in the second row, letter of S, and then 2 exponents, because we're going 1, 2. So our next part would be 2s2. That takes care of that and that. Continuing our way across the second row here. Now for this section, we're still in the second row, but these corresponded with a P sublevel, and we need all 6. So our next part would be 2P6, which did all of those. Next up, we're in the third row, where sodium and magnesium are, so that would be 3S2. And last but not least, the only thing we need to finish up is this piece right here. Third row, P sublevel, and only 1 spot. So our last part here would be 3P1. That's the full electron configuration for aluminum. Keep in mind, we mentioned that a way to check your work, if you add up all of these exponents, they should equal the atomic number, so they should equal 13 for aluminum, which they do. Okay? The next one, let's skip to C actually for a moment. C is similar. Now we're still dealing with an atom, but uranium's way farther down on the periodic table. So the electron configuration is going to be a lot lengthier. Okay? We'll do all the full ones first, and then we'll go back to the noble gas configurations. So if you were to write the full electron configuration, we can do that. The problem is, let me get this other one out of the way. The problem is we're going to have to go through the D and the F sublevels. And if you remember, we mentioned one weird quirk here. The D sublevels, you have to write them as 1 row less than they appear. The F sublevels, we write them as 2 rows less. So even though this one, for example, is in the 4th row, we would write this as 3D. And then however many spots over you would go. Okay? So uranium's all the way down here. It's the 92nd element. And these two, remember, technically fall in right here. So this uranium is technically in the 7th row. So we've got a ways to go here. Okay? So I'll go quickly at first, and then we'll get to the end. So starting off, it would start normally. So it would go 1s2, 2s2, 2p6. That finishes the 2nd row. Up to here would finish the 3rd row. Okay? Now, when we get to the 4th row, we'd start normal, 4s2. But remember, right here, we really are moving into the D sublevels, but rather than saying 4D, we're going to actually write it as 1 row less, so it would be 3D. If you count across, there's 10 spots. And then when we get over to gallium right here, we're back in a regular section, so instead of changing numbers or anything, it'll just do 4P. So we do 4P6. That finishes the 4th row. Now moving to the 5th. Here's that subtraction again for the D sublevels, then back to normal. Here's the 6th row, 6s2. Now here's where it gets weird as well. Rather than just doing 6s and then moving to 5d, in between there now, these 2 rows are falling right in here. So in these last 2 rows, it really goes S, F, D, and then P. Okay? Depending on which periodic table you use, sometimes it might get a little bit wonky here, but we write the F sublevels as 2 rows less. So we'll fill that whole first section there. So we'll do 4F14. Then we go back to the D sublevels, but we still write them as 1 row less, so 5D10. And then finishing out that 6th row would be 6P6. Okay? Now our last part, we'd finish the 7th row, start the 7th row, so 7s2, and then the question is how many spots in are we moving for uranium? Now on this one here, we're moving 4, alright, on this particular periodic table, there are 4, so I would end that with 2 subtracting by 2, so 5f4, but if you're using the periodic table from the reference book, you're going to have the one sort of hanging D electron, and then moving down, so it would be equally correct if you ended this with 7s2, 6d1, and then 5f3. That would be perfectly fine as well. Okay? So that one was long. The middle one was, that we skipped over a moment ago, was the sulfide ion. Keep in mind that the sulfide ion, we see sulfide right here, or sulfur right here. When it's an ion, it has a charge of -2, meaning it gains these 2 extra electrons to complete its octet. So if we're writing the electron configuration for the sulfide ion, you're really just writing the configuration for argon as an atom. So if I write that one, this one's going to be a lot easier compared to our uranium one we just did, but we'll just move our way through the 1st row, the 2nd row, the 3rd, and then we'll end with partway through the 3rd. Okay? That would have been the sulfur atom, but plus those 2 extra electrons, it would indeed be 3p6. Okay, so again, it's going to look a lot like argon. Now, the last part of this question asks you to write the abbreviated or noble gas configuration. So how do you do that? You pick the noble gas in the row above the element you're trying to write it for. You put that symbol in brackets, and then everything else that you would sort of just continue the same way you did. You're basically starting partway through the periodic table. So our aluminum atom, we erased this one before, but this would have been our electron configuration for aluminum. Right? If you look on the periodic table, you'll see that if you find aluminum, it's in the third row, the noble gas in the row above it is neon. So to write our noble gas configuration, I'm going to put neon in brackets, and then you continue after where neon left off. So the next part, if this neon's at the end of the second row, we start with the third row. So 3s2, 3p1. So again, you see the end of that. We're basically replacing this whole piece with just that, which makes your life a little bit easier. Same thing for the sulfide ion. Sulfur's in the third row, so neon happens to be the core for this one as well. So if we write the rest of it, we see 3s2, 3p6. The one where this is really going to be handy is uranium, because rather than writing this whole thing you see there, we would say that uranium's in the seventh row. So the noble gas in the row above it would be radon. So I'm going to write that, and then all we need to do is write everything that's left for the seventh row. So this whole part here would be what's left. So again, you could either say 7s2, 5f4, or if you're using the one in your reference booklet, 7s2, 61, 5f3. Either of those would be fine. Okay? So there's our electron configurations. These are a little tough to explain without a periodic table that I'm pointing to. So if you have more questions, just let me know. 13 asks you to draw orbital diagrams. So orbital diagrams is just another way to represent electron configurations. Okay, so I'm going to start with the electron configuration for both of these. So I'm just going to jot those out quickly. Hopefully we're all able to do that on our own by now. All right, there's the one, and then strontium is a +2 charge. So if it has a positive charge, it means it lost 2 electrons. So strontium had 38 protons and 38 electrons. If it loses 2 electrons, it would now have 36, which makes it look like krypton. So I'm really just going to be writing the electron configuration for krypton here. Which is at the end of the fourth row. Alright, so there we go. Now I wrote the full thing out. It tells us to draw the orbital diagram. Okay, to save us some space on here, I know it says in big bold letters, do not use the abbreviated shorthand, but we wrote out the full one for the electron configuration, so I think we can save ourselves some time and use the shorthand for the electron configuration here, or for the orbital diagram here. On the test though, if it says to use the whole thing, use the whole thing. Okay? But if I use the shorthand here, for the first one it's not that long, so we can do that one. Every piece of this configuration needs its own part in our orbital diagram. So anytime you see an S sublevel, they only have one orbital, so we drew that with one box, or you can do sort of one line. So we have one S. The 2s, still an S, so it's still just going to be one box. Now when we move to P, the P sublevel can hold 6 electrons, so it has 3 orbitals always. Okay, back to an S, so just one, and then P again could hold 6. So even though there's only 3 electrons, we still need to draw all of the possible orbitals. Then we just fill in our electrons. So the S sublevel has 2. Notice I'm doing one up, one down. That's because of the Pauli exclusion principle. And you have to completely fill an orbital, a sublevel before you move on. So when we get to 2p6 right here, technically they fill like this. 1, 2, 3, so all up. They fill all the empty seats, and then they go back and fill up those remaining pairs. 3s2, we just have to go up and down because there's only one seat. And then here's where you have to be really careful. So 3p3, according to Hund's rule, they have to fill like this. All the empty seats filled first. Okay? Electrons are all negative, so they don't want to be near each other if they don't have to. So that would be our orbital diagram for phosphorus. Okay? If we do it for the strontium atom, same thing. If we did this one in shorthand just so we could see it, the shorthand would be a little tricky because it's krypton. So actually let's just do the full thing for this one as well. So it's going to start off similarly. If you'd rather use boxes instead of just dashes like this, that's perfectly fine as well. Okay, 4s. Where this one's different is we now have 3d. D sublevels have 5 orbitals, so I need to draw 5 conjoined boxes there. And then P's again have 3, so there we are. So no matter what the coefficient is, the number of boxes you're drawing depends on the letter. Okay? So 1s would feel like that, 2s2, 2p6 would go 3 up and then 3 down, 3s would go like that, 3p would feel the same way. The reason I'm filling from the lowest to the highest, that's because of the off-ball principle, the idea that electrons fill from lowest sublevels to highest. Pauli exclusion principle is the reason I'm drawing one up, one down. Electrons have opposite spin. And then Hund's rule is why I'm filling them one at a time before they pair. The last one was 4p6. All of these will be filled, but they would have filled like this, all up and then all down. Okay, so there's our orbital diagrams in completion. Moving to 14, distinguishing ground state and excited state. You can certainly look these definitions up yourself. The key idea is the ground state is when all electrons in an atom are in their lowest energy levels, whereas an excited state means that one or more electrons are in energy levels higher than their normal ones, so they're in these temporary higher energy levels. Okay? Question 15, we were putting those formulas that we did way back in question, what was that, question 8? We're putting those to use. Okay, so you see here wavelength, which wavelength, remember, is this variable. You also see energy. So the question is, what formula has both of those? If you look at those three that you wrote back in that original question for this unit, or if you look in your reference book, you'll see the only equation that has both of those is this one, E equals hc over lambda. You could also do it in 2 steps, but this one saves you some time. The one thing you have to recognize, though, before you start plugging things in, c, remember, was the speed of light, and that's 3 times 10 to the 8th meters per second. Okay? So if this is 3 times 10 to the 8th meters per second, that means we need to match units with it, right? But notice here's a discrepancy. That's in meters, and this is in nanometers. So before we can plug into our equation, the first thing you need to do is do some quick dimensional analysis. So if I take 780 nanometers, we need to convert nanometers to meters, which we did back in unit 1. I always put a 1 with a larger unit, which would be the meter. Nano is 10 to 9th spots away from the meter, so we would say 10 to the 9th nanometers per meter. Also remember, if you forget how to do this, in the front page of your reference book you'll see some charts to help you out there, so please look at that. Okay, but that's our wavelength, newly converted. So now we just, oh, that looks like an X, one sec. There we go, that's the Greek letter lambda. So now we just need to plug into our equation and solve. Okay, so if E equals hc over lambda, h is a constant. It's straight out of the reference book. Okay, the unit on that is joules times seconds. And then here's our speed of light, again a constant. Alright, just plugging in again to this equation right there. And then our wavelength, which we just converted over there, 7.8 times 10 to the negative 7th meters. So if we check what cancels, seconds cancel, meters cancel, leaving us with just joules, which is what we wanted. So if you do all of your math here to 3 sig figs, because 780 only has 3 sig figs, you should get, wrong number there, you would get 2.5 times 10 to the negative 19th joules. So that would be the energy of 1 photon of light used in the CD player. Okay? So let's see, we just have a few more here. So our periodic properties, this you can color coordinate with your periodic table that we did in this unit. You'll also see some other ones in the notes. So I'm just going to take a picture of mine and overlay it, so give me 1 second for that. Alright, so there's the layout. You can see where everything is falling here. So we've got our alkali metals, alkaline earth metals, halogens, noble gases. Here are the metalloids. There are only 6. They're the ones touching the stair line. Metals are everything to the left of the stair line. Non-metals are to the right. Transition metals are the section in the center. And then this would be the lanthanide series. This would be the actinide series. So you can check all those out in a little bit more detail if you want to look at that a little bit more. Last but not least in this unit, we have our trends. So whenever we did a trends question, I suggested you always drew the arrows off to the side. What did I mean by that? Atomic radius, if you think of that acronym lower left, large, loose, the lower left are the largest, meaning if we're drawing the order of increasing atomic radius, I would draw this next to this, knowing that the trend increases going from right to left across a series or a period, and then it increases going down a group. So knowing that this is the general trend, if I find where these 4 particular elements are on the periodic table, the smallest one would be the one that was, the most up here. The largest one would be the most down there. So if we put these in order, that would look like this. Again, these are a little bit easier to explain if the periodic table is handy, but I suggest you draw the arrows. Ionization energy is the amount of energy needed to take an electron from an atom. And if you look back in what we wrote, we said that the trend increased up and to the right. The elements in the upper right corner, the ones that are the most electronegative, are the hardest to take electrons from. So they also have the highest energies because it's going to be the hardest to take them. So again, if we look sort of at this diagonal pattern increasing sort of upwards this way, if we put these 5 in order, the easiest to take an electron from would be barium. The most difficult would actually be magnesium. Okay, so there's our trends. So again, that was pretty long, but that's our Unit 6 questions. I will make the next video for our Unit 7, which will be molecular geometry. I would imagine this one will be a little bit quicker than the others.